Okay, welcome back to Special Topics of Semiconductor Technologies. Next, we are going to discuss in the Chapter 3, talking about the basics semiconductors device and processing. The objectives of this chapter will be the following. First, to identify at least two semiconductor materials from the periodic table of elements. Next, to list so-called N-type and P-type dopants. Next will be describe a diode and a MOS transistor. Then these three kinds of chip made in the semiconductor industry. The last will be list at least four basic processes required for chip manufacturing. The first topic we will discuss what is semiconductor. Then we'll discuss semiconductor device and the basics of IC processing. What is semiconductor? Semiconductor is a material. Its conductivity between conductor and insulator. It's not a conductor and it's not insulator, but somehow you can control the conductivity from insulator to conductor. Basically, it's an insulator. A semiconductor, its conductivity can be controlled by dopant. Dopant is the minor elements that is introduced into the semiconductor materials. A very minute material. Sometimes we say impurities. So that means the semiconductor, its conductivity is come from impurity. There are two types of single element type semiconductor material we are using right now. The first is the silicon. The other one is germanium. So you have silicon, you have germanium. These are element type semiconductor materials. Germanium is the first one used for semiconductor materials. And then 2 years later, the silicon single crystal. There's another kind of semiconductor material called compound semiconductor. Something like silicon germanium, silicon carbide, gallium arsenide, indium phosphate. And these compound semiconductor normally has a special application. For silicon and germanium, it's basically provide you the substrate, so you can build the semiconductor device on top of the substrate. All the property come from the design. But for the compound semiconductor, normally the property come from the electronic configuration by itself. On the periodic table, the basic materials or element can be used in semiconductor industry, basically with 4 in this group. The primary material will be in 4A group. The element in 4A group is carbon, silicon, germanium. Among that, silicon and germanium is two of the material has been widely used in semiconductor material, especially silicon right now, which will dominate the semiconductor industry more than 90%. Use silicon as the substrate. For the other materials, for example, group 3A, boron, aluminum, gallium, indium, etc. Group 3. On the right hand side, next to the silicon and germanium, group 5. Nitrogen, phosphorus, arsenic. These are the major materials used in the semiconductor material. And for the group 4 materials, silicon and germanium, they are used as the substrate. And for group 3 and group 5 materials, these materials are used as the dopant, the so-called impurity. The conductivity of semiconductor material primarily come from these dopants. So over here, the silicon can be a substrate, and the group 3 and group 5 are the dopants. For group 3 materials, which has one less electron less than the group 4 elements in the outermost electron shell, we call that a so-called p-type dopant. For group 5 material, phosphorus, arsenic, we call n-type dopant. The reason for p-type and n-type dopant is, for the p-type dopant, the primary charge carrier contributing to the conductivity is Hall. Hall with positive charge. That's why we call p-type. But for the group 5 elements, it has one more free electron than the group 4 elements. And the primary charge carrier contributing to the conductivity will be electron. Electron with negative charge. That's why we say it's a so-called n-type dopant. So this is the primary substrate material, silicon or germanium, and then p-type dopant and n-type dopant. Looking at an atom, basically you have electron circulating at orbit around the nucleus. The innermost electron here has a higher attractive force by the nucleus. The further away from the nucleus, the electron has more energy to move or to escape from the attractive force from the nucleus. In that case, we will describe the electron energy which is proportional to the distance from nucleus. So the further away from the nucleus has higher energy than the innermost electron. According to the Pauli exclusion principles, the electron will occupy at the orbital no more than 2 electrons per orbital, and those 2 electrons has different spin direction: top spin and down spin. Due to the different spin direction, the 2 electrons at the same orbital has slightly energy different. Based upon thermodynamics, all the electrons supposed to fill in the orbitals from the innermost orbital first, because it has lower energy than the outermost electron. So we will have lower energy orbital have electron filled in first, and then next one, and then next one. Where the outermost orbitals, which occupied by electron, it is so-called valence band. From a single orbital, single energy level to a valence band, it is because over here we are talking about single atom, but over here we are talking about a solid. For example, silicon single crystal. A solid is composed of numerous atoms. Those numerous atoms, based upon the Pauli exclusion principles, it will have formed a band of energy level instead of a single level of energy. So the outermost electron occupied by a certain energy level we call valence band here, EV. And the next energy band with higher energy level than valence band, we define that as conduction band. Conduction band EC. In between of the valence band and conducting band, this is called energy gap, EG. This is a forbidden area. No electron allowed at this forbidden gap. No energy level, no electron. So electron cannot just floating around at the energy gap unless you have somehow creating a new energy level, so electron can locate it on this new energy level. So no electron will stay in the energy band gap area. And this is the basically atomic structure and energy band structure of a solid. So remember that the outermost electron shell, electron orbital, occupied by electron is called valence band. The one with higher energy level above the valence band is called conduction band. In between is called energy gap, EG. Okay, based upon the energy level between the valence band and conduction band, we will be able to define the so-called conductor, insulator, and semiconductor. Basically, when you have first the conducting band and valence band overlapping together, when the electron has a very close distance with each other, a magnetic field will occur, and that will cause the energy band to split, to slip up with wider instead of small band, it become a wide energy band. So it could have another valence band here, which is overlapping with the conducting band. In that case, the two bands overlapping with each other, electron can easily move from valence band to conducting band over here, and we will say this is a conductor. To define a conductor, there's two criteria. The first will be electron in conducting band. Or second criteria, hole in valence band. This is two criteria that will define a material to be conductors. You have electron in conducting band, or you have hole in valence band. So as we mentioned, for the first case, you have conducting band and valence band split up with the wider band, and then cause overlapping here, so electron can move from valence band to conducting band. In that case, when electron move from valence band to conducting band, that it meet the first criteria, electron moving in conduction band. Because the electron move from valence band to conducting band, it will leave behind a hole in valence band. So in this case, it will meet both criteria. So in the case of aluminum, that is why aluminum is a conductor. Another case will be something like sodium. Sodium has 11 electrons. As we mentioned that each one of the orbit can be occupied by 2 electrons with different spin directions. So you can imagine that these 11 electrons will occupy totally 6 orbit. First orbit 2 electron, next one 2 electron, 2 electron, 2 electron. So we got 2, 4, 6, 8, 10 electron. It got only one left. So in this orbit, it got only 1 electron. But because of each of the orbit can occupy by 2 electrons, so you got another one vacant. Another vacancy. Do not have electron. This is how we define the so-called hole. So you have electron, you have hole at this specific energy level. So at this energy level, that means you have half of the orbit occupied by hole. The other half is free of electron. Okay, this is occupied by electron, the other will be hole. No electron at the first state. But since this is the same orbit, that means electron can move from this position to next position, exchange the position with the hole. So that means you have half field valence band. The other half will be hole. So in this valence band, you have hole inside. That will meet the second criteria where we define the conductor. You have hole in valence band. So in the case of sodium, the reason it is a conductor because it's a half filled. Over here, the valence band is half filled. So you have hole inside, so it's a conductor. So now you have the idea why you have conductor, either overlapping of valence band and conducting band, or only half filled in the valence band. On the other hand, let's look at the silicon dioxide. Some material has valence band and conducting band separating by a large energy gap. In general, if you have energy gap greater than about 4 electron volt, it's quite a large energy gap. So it will be very difficult for electron at the valence band receive energy and jump from low energy level to high energy level. Electron actually can jump from low energy level to high energy level if you supply the energy. That energy can be heat, can be electromagnetic radiation. But when you have energy gap larger than 4 electron volt, it's basically very difficult for electron jumping from low energy level to high energy level, creating an electron and hole pair. When electron jumping from valence band to conducting band, electron become moving at conducting band and leave behind a hole, so we call this electron hole pair. And this electron hole pair, both electron and hole will contributing to the conductivities. But things you have very large energy band gap, so the opportunity, the probability for electron jumping from low energy level to high energy level will be very, very slim. So basically, it's an insulator. But in the case of semiconductor, for example, silicon has energy band gap equal to about 1.1 electron volt. When you have material with energy band gap somewhere less than 2 electron volt, you got a very good opportunities. The electron can jump from valence band to conducting band, form an electron hole pair, contributing the conductivity. And for silicon, the energy band gap is 1.1 electron volt, so it's less than 2 electron volt, so it got a chance to become conductive. So initially it is filled at the valence band and empty, no electron at conducting band. So it's supposedly it is an insulator, but because energy band gap is less than 2 electron volt, so it got very good probabilities that after receiving energy from outside, electron can move from here to here and form electron hole pair, and these two will contributing the conductivity for silicon. Okay, now we'll conclude our first part of chapter 3. We discussed what is semiconductor, how to define conductor, semiconductor, and insulator.